as we continue to look at the inverse of a function, we're going to start to look at how do I find the inverse of a function, either graphically or through algebraic means. If I'm going to look at it graphically, the way that we find the inverse is we reflect the graph over the line y equals x, which, if we remember our symmetries, if we reflect over y equals x, then xy is going to become yx. If you think about it, it makes a lot of sense. The inverse swaps the x's and the y's. My input becomes my output, and output becomes my input. So if we look at an example or two here, I'm going to graph each function and then use the symmetry to graph the inverse. So my original x to the third, we know that he's the parent graph. He goes through 0, 0, 1, 1, 2, 8, and -1, -1, and -2, -8. So that's all f of x, my original. So I get a pretty nice looking cubic graph right there. And if I think about how I'm going to get the inverse, I reflect it over y equals x. I use that symmetry I listed above. So f inverse of x is going to be 0, 0, 1, 1, 8, 2, -1, -1, and -8, -2. So if I apply those right here, 0, 0, 1, 1, 8, 2, some of the points don't really change, but when I pull out them all, I end up getting a function that looks like this. If I can draw it well, comes up, goes through there, and goes up that way. That's f inverse of x, which, if we remember from our parent graphs, is actually just the third root of x, which makes sense. If I want to undo x to the third, I use the third root. But if you notice, these are reflected across the line right here, y equals x. So I'm reflected across that line, if I could draw it straight. For my second example, I have the square root of x minus 2, which is a square root that's been moved right 2. So f of x, I have 2, 0. Now you could find some more of these by plugging some values in or tracking some important points. I'm just going to state what they are: 3, 1, 6, 2, and I think that's all of them that I can fit onto this graph right now. So there's my original function, f of x. I go through and apply the symmetry by swapping the x's and the y's. So f inverse of x is going to be 0, 2. It's going to be 1, 3. It's going to be 2, 6. And if I connect those, I get that part of the graph right there. So that's f inverse. And if I look, I have reflected it across the line y equals x. Now you may expect the inverse of a square root to be some sort of squared function. And I do have some sort of squared, but in this case, I only have half of my quadratic. The other half would go like that, and we're going to look at here in a second why I only get half of the function. But I do get an inverse that is a quadratic, but I get half of a quadratic as my inverse function. So graphically, I want to use the reflection y equals x and go ahead and get my inverse that way. The problem is I don't always have a nice graph to work with, so we're also going to look here at how do I do this algebraically? How do I get the equation of my inverse? So my steps, I'm going to fill them all in here, that way I don't have to scroll back and forth, but then I'll talk through them as I go. The steps are, I'm going to go through and rewrite the function as y equals instead of f of x equals. After that, I'm going to switch the x's and y's, literally switch where they're at, and solve for y. What this is doing is it's switching the x's and y's like inverses do. And then I'm going to check the domain and range of the original and inverse functions. I'll do that as I go. For the inverse functions, the domain and range actually swap, and we'll explain why here soon. So we're going to use this to check for domain restrictions for inverse functions, especially with quadratic. Quadratic functions have the possibility of having those domain restrictions. That's the only really important one that I want to point out here. There might be a little bit more, but we're going to stick with just quadratic. So example 1. I'm going to go about this in a pretty regimented way. So here's f of x. I want to sketch what his graph looks like. And when I say sketch, I mean I just want shape and a couple pieces of information. So f of x is 2x plus 3. He's just a line that goes up like that, and he hits at 3. His domain and range are both going to be negative infinity to infinity. So following my steps, I want to go ahead and rewrite him as y equals 2x plus 3. And then I swap the x and the y. I just change their locations. So it's x equals 2y plus 3. Next, I solve for y. So I'm going to subtract 3 over. X minus 3 equals 2y. Divide everybody by 2. I get x minus 3 over 2 equals y. So that's my inverse function. Right here, I'm going to write it as f inverse of x equals, I'm going to break up this fraction into a 1/2 x minus 3/2, just so he looks like slope-intercept form. You could leave it as x minus 3 over 2. It's just going to help me here in a second when I graph. So there's my inverse function. That's the function that will undo this original. And think about it. In the original, you multiply by 2 and then add 3. With the inverse here, you go backwards. You subtract 3 first, and then you divide by 2. You're undoing things backwards. So if I look at what f inverse of x looks like, let me get a blue here. Here we go. He's going to go down like that. If I were to put them on the same graph, I would notice that they are inverses. They are reflected across y equals x. And the domain and range of this guy is negative infinity to infinity because he's linear. So there's my inverse function, and there's my domain and range for each the original and the inverse. Linear is a pretty straightforward example because the inverse of a linear is a linear. In example 2, we have a cubic function. So I'm going to start out by sketching a little bit of f of x. I know he's right 2 up 4. So maybe that's about there, not drawn to scale. And it comes up and goes up through like that. His domain and range, let me trace them in green here just so I'm consistent. There we go. Domain and range are both going to be negative infinity to infinity. So let's follow my process. Write it as y equals x minus 2 to the third plus 4. Swap the x and the y. So x equals y minus 2 to the third plus 4. And now I need to start solving for y. So I subtract 4 first. That equals y minus 2 to the third. I'm working inside out toward that y. So the next guy I have to deal with is that third power. I do that by taking a third root of each side. So the third root of x minus 4 equals y minus 2. I'm almost there. Add the 2 over. So I have the third root of x minus 4 plus 2 outside of the radical equals y. I can now read off my inverse. Notice how I like to write it as f inverse of x equals, not really the y because there was no y in my original. So f inverse of x equals the third root of x minus 4 plus 2. That's my inverse function. And if I look at what he looks like, I'm going to have a cubic that's moved right 4 up 2. So right 4 up 2. And he's going to come up through like that. So that was at 4, 2. If I go back to that original, that was at 2, 4. You don't have to label those kind of points. The picture is more for me just figuring out what the domain and range are. So the domain and range in this case are going to both be negative infinity to infinity. So we haven't had to run into any situations where we deal with the domain and range yet. My focus right here on these is just looking at what is the inverse of the function. And it makes sense that the inverse of a cubic is a cubed root. And if you look at what's happening to the cubic, you are subtracting 2, raising to a third, and then adding 4. Do those things, undo those things backwards. You're subtracting 4, you are taking a third root, and then you're adding 2. It just makes sense to undo them in the opposite order that you do them. We're going to stop there for this video, and we're going to pick up in the next one with the rest of our examples on finding inverse functions.